Instead of following established analytical paths, the focus is placed on reimagining foundational mathematical objects, identifying hidden symmetries, and examining the consequences of these ideas rigorously. The first such reimagining is applied to the imaginary unit. The imaginary unit is redefined using a logarithmic expression, specifically as the natural logarithm of 2. From this definition, logarithmic identities are applied to express the logarithm of -1 in terms of the logarithm of the imaginary unit. This construction introduces a logarithmic structure into the imaginary unit itself. The intention behind this redefinition is to create a framework in which new symmetries of the Riemann zeta function can be examined using logarithmic transformations rather than purely algebraic ones. Building on this idea, attention is then directed toward the symmetries of the zeta function. Classical theory recognizes reflection symmetry around the line where the real part of the complex variable equals 1/2. In this approach, additional symmetries are sought by applying logarithmic transformations. These transformations are used as tools to reveal structural behaviors of the zeta function that may not be apparent through traditional formulations. The discussion then turns to the pi function. The pi function is defined as a shifted form of the gamma function, specifically as the gamma function evaluated at the argument +1. This definition generalizes the factorial function to complex numbers. For complex arguments whose real part is greater than -1, the pi function admits an integral representation involving an exponential decay factor and a power of the integration variable. This establishes pi as a natural extension of the factorial concept beyond the integers. Using this integral definition, the recurrence relation of the pi function is derived. The derivation proceeds by evaluating pi at the argument +1 and applying integration by parts. The exponential decay ensures that boundary terms vanish at both 0 and infinity. The remaining integral reproduces the original pi function multiplied by the argument +1. This leads directly to the recurrence relation showing that pi of s plus 1 equals s plus 1 times pi of s. This mirrors the classical factorial recurrence. The singular structure of the pi function is then examined. Its poles arise from the poles of the gamma function and occur at negative integer values shifted appropriately. A local Laurent expansion describes the behavior near these poles. Reflection formulas involving the sine function are invoked to characterize the residues, allowing the singularities to be treated in a controlled analytic manner. The gamma function itself is then introduced as a generalization of the factorial function to complex numbers. For complex arguments with positive real part, it is defined by an improper integral involving a power of the integration variable multiplied by an exponential decay factor. This function plays a central role in complex analysis and serves as the backbone of the factorial family. The recurrence relation of the gamma function is derived next. By evaluating gamma at the argument +1 and applying integration by parts, the boundary terms again vanish due to exponential decay. The resulting expression shows that gamma of s plus 1 equals s times gamma of s. This recurrence establishes consistency with factorial behavior on the integers. The poles of the gamma function are then described. The function has simple poles at all non-positive integers. Near each pole, the gamma function admits a Laurent expansion with a simple principal part. Reflection identities involving sine functions are used to describe how residues are determined and how these singularities fit into the broader analytic structure. Following this, the delta function is introduced. The delta function is defined as another shifted form of the gamma function, obtained by shifting the argument downward by one additional unit compared to pi. It is represented by an integral involving a power of the integration variable reduced by 2 and an exponential decay factor. The naming of the function is explained as part of a conceptual cycle completing the factorial family. The recurrence relation for the delta function is derived through repeated application of integration by parts. The derivation shows that delta evaluated at the argument plus 2 can be expressed as the product of two linear factors multiplied by delta at the original argument. This places the delta function firmly within the factorial family, with its own consistent recurrence structure. The analytic properties of the delta function are then outlined. Like the gamma function, delta is analytic except at specific negative integer values where it has simple poles. The residues at these poles follow a pattern analogous to those of the gamma and pi functions. This confirms that delta inherits its singular behavior from the gamma function through argument shifting. An explicit interfunctional relationship is then presented. The pi function, gamma function, and delta function are shown to be equivalent up to shifts in their arguments. Specifically, pi evaluated at a given argument equals gamma evaluated at that argument plus 1, and also equals delta evaluated at that argument minus 2. This identity unifies the three functions as different representations of the same factorial structure. The discussion then generalizes further by defining a generalized gamma function indexed by an integer shift. This generalized function is defined as the gamma function evaluated at the argument minus a fixed integer. An integral representation is provided, extending factorial-type behavior across an entire family of shifted functions. The recurrence relation for the generalized gamma function is derived using integration by parts. The result shows that the recurrence structure persists across all members of the family, with the multiplicative factor adjusted according to the shift parameter. This demonstrates that the factorial mechanism remains intact under generalized shifts. The pole structure of the generalized gamma function is then examined. The poles occur at integer locations determined by the shift index. Laurent expansions describe the behavior near these poles, and reflection formulas are used to determine residues. This establishes a consistent meromorphic structure for the generalized family. The work then introduces inverse type functions. An inverse pi function is defined using an integral over the negative real axis. By applying a substitution, the integral is transformed into the standard pi function, evaluated at a shifted argument. This shows that the inverse pi function is functionally equivalent to the pi function rather than a true algebraic inverse. A recurrence relation for the inverse pi function is derived using integration by parts. The resulting relation mirrors that of the standard pi function. The pole structure of the inverse pi function is also described, with poles occurring at negative integer values and residues determined through reflection identities. An inverse gamma function is then defined in a similar manner. Its integral representation over the negative real axis transforms directly into the standard gamma function. As a result, the inverse gamma function coincides analytically with the gamma function itself. Its recurrence relation and pole structure follow immediately from this equivalence. The inverse delta function is introduced next. Through substitution, its defining integral maps to the delta function evaluated at a reflected argument. A recurrence relation is derived, and the poles of the inverse delta function are shown to occur at positive integers, with residues determined using reflection formulas. The construction is extended further by defining an inverse generalized gamma function. Its integral representation maps directly to a shifted gamma function. A recurrence relation is obtained, and the pole structure is shown to mirror that of the gamma function under reflection, establishing a consistent inverse framework across the generalized family. At this point, the factorial family is unified conceptually. The pi, gamma, and delta functions, along with their inverse and periodic counterparts, are presented as deeply interconnected objects. Periodicity and harmonic behavior are emphasized as central themes. The functions are described as forming a tightly coupled system, rather than isolated entities. The role of periodicity and harmonicity within the unit circle is then explained. Functions defined on or related to the unit circle exhibit repeating behavior due to the nature of complex exponentials. Inverses in this setting are influenced by periodic structure rather than simple algebraic reversal, requiring careful interpretation. Symmetry around zero is then discussed. The factorial functions and their inverses do not exhibit simple symmetry due to the involvement of sums of multiple functional components. This complexity explains why additive or multiplicative inverses are not straightforward in this framework. A numerical table is presented to illustrate symmetry relationships among the factorial family and their inverses. The table demonstrates structured numerical patterns that reflect the underlying functional symmetries. Finally, the discussion moves toward the zeta function. A family of alternate functional equations is introduced, each involving different variants of factorial type functions. These equations preserve reflection symmetry, while incorporating generalized gamma functions and shifted zeta functions. This prepares the groundwork for further lemmas and proof-oriented development related to the Riemann hypothesis. With the foundational framework in place, the focus transitions from definitions toward proof-oriented development. The objective at this stage is not to present a final conclusion, but to construct the analytical tools required for deeper exploration of the Riemann hypothesis. The factorial family of functions introduced earlier is now treated as a functional system capable of supporting such analysis. The classical forms of the gamma and pi functions are revisited to ensure continuity. Euler's original integral definitions are recalled, emphasizing convergence conditions, analytic continuation, recurrence relations, and pole structures. These properties are not restated for validation, but to establish a consistent reference baseline for subsequent transformations. Attention is then returned to the delta function. The delta function is emphasized as an extension of factorial behavior into domains traditionally associated with singularities. By carefully shifting the argument and analyzing its integral form, the delta function allows controlled traversal across negative integer values. Its recurrence relation is revisited to show how factorial growth is preserved, even when the argument moves deeper into the negative domain. The conceptual motivation behind introducing multiple factorial variants is then clarified. Each variant offers a distinct perspective on symmetry, recurrence, and reflection. Rather than viewing pi, gamma, and delta as separate entities, they are treated as different coordinate views of the same underlying structure. This perspective allows transformations between them without loss of analytic information. The generalized gamma family is then applied directly to zeta function expressions. By pairing the zeta function with different shifted gamma functions, a collection of modified functional equations emerges. Each equation preserves analytic equivalence while altering the symmetry frame through which the zeta function is examined. The reflection principle is revisited in this expanded context. Instead of a single reflection across the critical line, multiple reflections appear depending on the factorial variant used. These reflections are governed by shift parameters and periodic components introduced earlier. This leads to a broader symmetry landscape in which the zeta function operates. Periodic behavior becomes increasingly important at this stage. The exponential terms inherent in gamma-type integrals introduce periodic modulation when evaluated on complex arguments. These oscillations interact with the zeta function's analytic structure, producing repeating patterns that align with the previously discussed unit circle framework. The inverse factorial functions are then reintroduced as symmetry complements rather than algebraic inverses. Their role is to balance forward growth with reflected decay. When combined with generalized gamma functions, they provide a mechanism for tracing analytic behavior across both positive and negative domains without discontinuity. The discussion then turns toward convergence control. By selecting appropriate factorial variants, divergent components of zeta-related expressions can be regulated. The factorial terms act as analytic dampers, ensuring convergence in regions where direct evaluation would otherwise fail. This mechanism relies on exponential decay rather than cancellation. At this point, the work introduces structured lemmas. These lemmas formalize relationships between shifted zeta functions and factorial families. Each lemma establishes equivalence between two analytic expressions under a specific transformation. The purpose of these lemmas is to create a chain of equivalences rather than isolated identities. The cumulative effect of these equivalences is a layered symmetry. Instead of a single axis of symmetry, the zeta function is shown to admit multiple symmetry axes depending on the factorial context applied. These axes intersect at critical points, creating a lattice of analytic balance. The critical line emerges naturally within this lattice rather than being imposed externally. Its role is described as a convergence boundary where multiple factorial symmetries coincide. At this boundary, growth and decay terms reach equilibrium under the transformations defined earlier. The discussion then emphasizes that zeros of the zeta function are examined through this equilibrium condition. Rather than testing zeros directly, the approach analyzes whether imbalance is possible under simultaneous factorial transformations. If imbalance cannot persist, zeros must align along the equilibrium boundary. This framework does not rely on numerical verification. Instead, it relies on structural consistency across the factorial family. The recurrence relations, pole alignments, and reflection properties jointly restrict where analytic cancellations can occur. As the argument develops, attention is given to the behavior of residues. Residues from poles introduced by factorial terms are shown to cancel or mirror under symmetry transformations. This ensures that no artificial zeros or singularities are introduced by the method itself. The interplay between additive and multiplicative structures is also highlighted. Logarithmic representations introduced at the beginning resurface here, allowing multiplicative behavior to be analyzed additively. This transition simplifies symmetry tracking across transformations. The narrative then returns briefly to the redefinition of the imaginary unit. Its logarithmic formulation is used to explain how phase rotation interacts with exponential decay. This provides a consistent phase framework across all factorial variants. Finally, the section concludes by positioning the developed machinery as sufficient for addressing the core analytic constraints of the Riemann hypothesis. The factorial family, generalized and inverted, forms a closed system capable of expressing zeta symmetries without contradiction. The analysis now proceeds by consolidating the symmetry framework into a single coherent perspective. Rather than treating each factorial variant in transformation independently, they are assembled into a unified analytical environment. Within this environment, every shift, reflection, and recurrence operates under a common structural logic. The zeta function is examined as an object embedded within this environment. Its analytic continuation is not viewed as an extension added afterward, but as a natural consequence of the factorial framework surrounding it. The generalized gamma functions provide the necessary analytic bridges across regions where the Dirichlet series representation alone is insufficient. Attention is then given to the behavior of the zeta function under complex conjugation. The factorial terms accompanying zeta expressions are shown to preserve conjugate symmetry. This ensures that analytic balance is maintained when moving between conjugate points in the complex plane. The functional equations derived earlier are revisited collectively. Each equation is shown to be a manifestation of the same underlying symmetry principle, expressed through different factorial lenses. When viewed together, these equations form a closed loop of equivalences, reinforcing internal consistency. The role of exponential decay is emphasized once more. Exponential terms arising from factorial integrals dominate polynomial growth in critical regions. This dominance ensures that transformed zeta expressions remain bounded where uncontrolled growth would otherwise occur. The discussion then addresses boundary behavior explicitly. As the real part of the complex variable approaches extreme values, factorial damping becomes increasingly significant. This behavior constrains the analytic freedom of the zeta function, narrowing the regions where non-trivial behavior can arise. The interaction between poles and zeros is examined in this constrained setting. Poles introduced by factorial terms are matched by corresponding zeros under reflection. This matching prevents the creation of asymmetrical singular behavior across the complex plane. At this stage, the argument highlights the impossibility of isolated imbalance. Any deviation from symmetry introduced at one point necessarily propagates through the factorial recurrence network. Because the network is closed, such deviations cannot persist without contradiction. The critical line is again interpreted as a structural attractor. Transformations applied off the line tend to redirect analytic behavior back toward equilibrium. This is not described as motion, but as constraint enforced by recurrence and reflection. The factorial family is then described as enforcing conservation of analytic weight. Growth in one region must be offset by decay elsewhere. This conservation principle limits the freedom of zero placement. The zeta zeros are therefore framed as equilibrium points of this conservation system. Only locations satisfying all factorial symmetries simultaneously can support cancellation without contradiction. The narrative then reinforces that this conclusion arises from structure rather than computation. No numerical approximation is required to enforce alignment. The constraints emerge directly from analytic identities. The generalized gamma functions are shown to act as regulators. By shifting arguments and reflecting domains, they expose hidden dependencies between different regions of the complex plane. The inverse factorial constructions complete this regulatory system. They ensure that backward traversal through transformations preserves analytic equivalence, rather than introducing artifacts. At this point, the framework is described as closed. No additional functions are required to maintain symmetry, convergence, and reflection. Every component introduced earlier plays a specific role within this closure. The concluding perspective emphasizes coherence. By reframing classical objects through generalized factorial symmetries and logarithmic structure, a consistent environment is constructed in which the behavior of the zeta function is tightly constrained. Within this environment, analytic balance emerges naturally, guiding the placement of non-trivial zeros. The framework concludes by emphasizing that every construction introduced serves a structural purpose. The logarithmic reinterpretation of fundamental quantities, the expansion of the factorial family, and the systematic use of recurrence and reflection are not isolated ideas. They function together as components of a single analytical system. Within this system, the Riemann zeta function is no longer treated as an isolated series or product. It is embedded within a network of transformations that regulate growth, decay, symmetry, and phase. The generalized factorial functions act as anchors, fixing analytic behavior across the complex plane. The functional equations derived throughout the work are presented as consequences of this embedding. Each equation reflects the same invariant structure, expressed through different parameter shifts and reflections. Their consistency reinforces the internal closure of the system. The presence of poles is treated as an unavoidable feature rather than an obstacle. Through careful alignment of factorial variance, pole contributions are controlled and balanced. Residues propagate symmetrically, preventing asymmetric divergence. The logarithmic structure introduced at the beginning reappears in the final synthesis. Phase relationships governed by logarithms ensure that rotations in the complex plane are tracked consistently across all transformations. This preserves coherence between exponential decay and oscillatory behavior. The factorial recurrence relations enforce continuity. Moving forward or backward through argument shifts does not disrupt analytic balance. Instead, each step preserves equivalence within the unified framework. The final interpretation emphasizes constraint rather than assertion. The analytic environment constructed restricts where imbalance can exist. Within these restrictions, equilibrium emerges naturally without external enforcement. The placement of non-trivial zeros is therefore framed as a consequence of structure. Only positions compatible with all factorial symmetries, reflections, and recurrences can sustain cancellation. Any alternative placement would violate the closed system of identities. This chapter is titled Results and Discussions. It begins by presenting outcomes derived from an induction-based approach applied to the Riemann zeta function and related infinite sums and products. The first subsection addresses the claim that the infinite product of positive zeta values converges. The discussion starts by writing the zeta function at 1 as an infinite harmonic series. This series is then rewritten as a product of geometric series indexed by prime powers. Similar expansions are written for zeta at 2 and zeta at 3, where each zeta value is expressed as a sum over reciprocals of integer powers, and then reorganized into products of geometric series. The product of zeta at 1, zeta at 2, zeta at 3, and so on is then considered. This product is expanded from the perspective of infinite sums over natural numbers raised to increasing negative powers. When these sums are multiplied together, terms are grouped according to common bases. This regrouping leads to a decomposition where each natural number contributes its own geometric series. The resulting expression is simplified step by step. The contribution from the integer 1 produces a constant term, while higher integers contribute infinite geometric sums. These sums are then combined to form an expression involving zeta at 1. The simplification leads to a final expression written as 1 plus zeta at 1. The same product is then analyzed from the perspective of primes instead of all natural numbers. Each prime contributes a geometric series. The contribution from the prime 2 simplifies first, producing a factor of 2. Subsequent prime factors are reorganized, eventually leading to a final expression equal to 2 times zeta at 1. This expression is then evaluated as equal to 2. The text then states that this value matches the sum of reciprocals of triangular numbers. The triangular numbers are defined as the sum of the first n natural numbers. The infinite series of reciprocals of triangular numbers is written explicitly, and then simplified using partial fractions. Each term is rewritten as a telescoping difference. When partial sums are computed, intermediate terms cancel, leaving a simple expression depending on the upper limit. Taking the limit as the upper bound goes to infinity yields a finite value of 2. This confirms that the infinite series of reciprocals of triangular numbers converges to 2. The next subsection claims that the infinite product of negative zeta values converges. The zeta function at negative integers is written as divergent power sums. These sums are again rewritten as products of geometric series for each integer base. Products of zeta at -1, -2, -3, and so on are formed. The expansion is carried out from the perspective of sums over natural numbers raised to positive powers. These sums are rearranged and rewritten using shifted series that subtract constant terms. Through successive algebraic regrouping, the expression is rewritten in terms of zeta at 1 and zeta at 0. Substituting known values leads to a final value of 1/2. The same product is then computed from the perspective of primes, producing the same numerical result. From this, the text concludes that zeta at -1 equals 1/2, stated as an alternative value alongside the classical value -1/12. The functional equation of the zeta function is then rewritten using the delta function instead of the gamma function. Equivalent expressions are then written using gamma and pi functions. Substituting s equals -1 into the functional equation yields the value 1/2 again, reinforcing the earlier result. The text then presents what is referred to as Ramanujan's method. A divergent sum of all natural numbers is denoted by a symbol. A shifted version of the same series is constructed, and subtraction is performed formally. This leads to an expression involving an infinite sum of ones, which is then assigned the value -1/2, producing a final result of 1/2. The next subsection states that the infinite sum of positive zeta values converges. Zeta at 1, 2, 3, and higher are written explicitly. These sums are grouped and rearranged. The total sum is expressed as zeta at 1 plus zeta at 0, which evaluates to 1/2. A similar argument is then applied to the infinite sum of negative zeta values. Zeta at -1, -2, -3, and so on are added together. The sum is again reduced to zeta at -1 plus zeta at 0, which evaluates to 0. The next subsection states that the infinite product of all zeta values converges. The product over all negative and positive zeta values is written compactly. Substituting the previously obtained values leads to a final product equal to 1. This is followed by a claim that the infinite sum of all zeta values converges. Adding all negative and positive zeta values yields 1/2. The next subsection presents a counterargument to Nicole Oersma's proof of divergence of the harmonic series. Oersma's comparison method using powers of 2 is reproduced. The harmonic series is shown to dominate another divergent series composed of repeated fractions. The text then rewrites the right-hand side using alternating summation techniques. By assigning a finite value to an alternating series, the right-hand side evaluates to 1. From this, it is argued that the harmonic series may converge to 1 if zeta at 1 is taken to be 1. Residue theory is then invoked. The Laurent expansion of the zeta function around its pole at 1 is described. The residue is identified as 1. It is argued that interpreting zeta at 1 as divergent is arbitrary. Since the pole lies on a zero radius of convergence, both infinity and 1 are presented as equally valid values. This leads to the interpretation of the zeta function as multivalued at this point. This interpretation is then used to assign the harmonic series the value 1. The next subsection introduces an integral representation of zeta at 1. The zeta function at 1 is written as a negative of an integral involving 1 over exponential minus 1. This integral is rewritten using an exponential series expansion. The integrand is expressed as an infinite sum of exponentials, and the order of summation and integration is exchanged. Each term of the series is integrated separately, producing a sum of reciprocals of natural numbers. This reproduces the harmonic series with a negative sign. A substitution is then performed by fixing the variable to the logarithm of 2 and changing the integration limits. Under this substitution, the integral evaluates to 1, leading to the assignment zeta at 1 equals 1. The following subsection provides an integral representation of zeta at minus 1. The expression begins with a contour-style integral involving a function evaluated at imaginary arguments divided by an exponential term. The integrand simplifies to a linear function of the variable, divided by an exponential minus 1. A change of variables rescales the integral into a standard form. The resulting integral evaluates to pi squared over 6, which leads to a final numerical value of 1/2 for zeta at minus 1. The next subsection discusses negative even zeta values and their reinterpretation of classical trivial zeros. Euler's reflection formula for the gamma function is applied inside the Riemann functional equation. Through algebraic manipulation, the functional equation is rewritten into a form involving the reciprocal of the gamma function and a cosine term. This rewritten form is then evaluated at specific negative even integers. Substituting values such as -2, -4, -6, and -8 produces explicit non-zero numerical values involving odd positive zeta values divided by powers of pi. These values are listed numerically, and the pattern is stated to continue indefinitely for all negative even integers. The next subsection introduces negative odd zeta values obtained from what is referred to as a harmonic conjugate of the functional equation. A modified functional equation is written, and specific substitutions are made for negative odd integers. This produces explicit rational values such as 1/2 minus 1/6, 1/6 minus 3/10, and so on. The continuation of this pattern for all negative odd integers is stated. A short subsection then notes that this harmonic conjugate functional equation also produces trivial zeros at negative, even integers due to the sign term present in the equation. The next subsection presents normalized negative, even values derived from another application of Euler's reflection formula. The functional equation is rewritten again, using a different gamma identity. This leads to a modified expression where an additional linear factor appears in the numerator. Evaluating this normalized form at negative even integers produces new numerical values expressed in terms of odd positive zeta values and powers of pi. These values are listed explicitly, and the continuation of the pattern to negative infinity is stated. Another subsection introduces yet another harmonic conjugate functional equation. By shifting the argument of the zeta function, a new equation is proposed that relates positive odd zeta values and negative, even zeta values within the same framework. Specific substitutions are made. Positive odd zeta values are expressed as powers of pi with integer coefficients. These expressions are then substituted into previously derived formulas for negative, even zeta values. This leads to integer results such as 1 minus 6 minus 60 and 2520. The pattern is stated to continue indefinitely. After a page break, the next subsection discusses rotation of numbers using Euler's formula. a modified unit circle representation is introduced, involving an exponential scaled by 1/2. Multiple branches of the imaginary unit are discussed, arising from higher powers of the imaginary unit cycling between 1 and -1. Using Euler's formula, logarithmic identities are constructed that relate exponential expressions, logarithms, and the imaginary unit. Several identities are written that parallel the classical identity e to the power I pi plus 1 equals 0. Numerical approximations are provided for exponential expressions involving pi and logarithms. The next subsection introduces what is called a fundamental formula of numbers. A theorem is stated relating the infinite sum of natural numbers to the infinite product of primes. The derivation begins by equating zeta at -1 with the sum of zeta at 1 and zeta at 0. Series expressions are rearranged term by term. Ratios of consecutive integers are formed. These ratios are then interpreted as a ratio between the sum of natural numbers and the product of prime numbers. This leads to the stated identity that twice the infinite sum of natural numbers equals the infinite product of primes. An auxiliary explanation is given using least common multiple arguments. Prime powers are accumulated and simplified, resulting in the product of all primes. The final subsection connects the presented zeta results with the prime number theorem. The prime counting function is introduced along with its asymptotic form. The role of Euler's number is recalled through its limit definition. Additional limits involving logarithms of 2 are introduced and connected to exponential growth and decay. Nested logarithmic expressions are presented, suggesting a recursive structure. This structure is described as generating self-replicating patterns. The chapter concludes by stating that this framework connects logarithms, the imaginary unit, the zeta function, and prime distributions into a unified structure. It is claimed that this structure allows deeper exploration of complex numbers and analytic behavior without requiring further extensions. This chapter is titled Proof Just by Words in PNT Limit. It states that the goal is to address several major number theory conjectures using verbal reasoning rather than formal derivations, with the prime number theorem, abbreviated as PNT, serving as the primary guiding principle. The opening section announces that the arguments rely on what is called a reverse prime number theorem limit. The intention is to treat average prime behavior as a structural constraint rather than a statistical approximation. The first subsection addresses Goldbach's prime theorem. The statement claims that every even integer greater than 2 can be written as the sum of two primes. The proof begins by considering an arbitrarily large number n. The sum of all natural numbers up to n is written as n times n plus 1 divided by 2. This sum is said to include the sum of all primes up to n as part of it. Doubling this total produces n times n plus 1, which is then described as containing twice the sum of all primes up to n. The prime number theorem is then invoked. According to the text, there are approximately n divided by the logarithm of n primes less than or equal to n. From this, the average prime gap is taken to be the logarithm of n. The quantity n over logarithm of n is then treated conceptually as if it were a single representative prime. The prime gaps are described as being adjustable or consolidatable into this single object. A logarithm is taken with base n over logarithm of n of the quantity n times n plus 1. This logarithm is interpreted as a lower bound on the exponent needed for powers of this representative prime to reach the size of n times n plus 1. Two primes p1 and p2 are introduced. p1 is bounded above by n over logarithm of n. p2 is bounded above by the logarithmic expression. These primes are set to sum to an even number e. The inequality involving powers of p1 is used to argue that the exponent exceeds 2. Because this exponent exceeds 2, it is said to exceed the minimal prime gap of 2. This is interpreted as guaranteeing continuity of the pattern indefinitely. From this continuity, the text concludes that all even numbers greater than 2 can be written as the sum of two primes. The statement declares that Goldbach's conjecture is therefore proved and may be renamed Goldbach's theorem. It is also stated that the weaker ternary version follows immediately. The next subsection is twin prime theorem. The statement claims that there are infinitely many primes p such that p plus 2 is also prime. The proof refers directly back to the Goldbach result. Since the logarithmic expression discussed earlier is greater than 2, the text states that infinitely many prime pairs with a gap of 2 must exist. From this, the twin prime conjecture is declared proved and renamed the twin prime theorem. The next subsection is Sophie Germain's prime theorem. The statement claims that there are infinitely many primes of the form 2 times p plus 1. The proof again relies on the existence of infinitely many twin primes with gap 2. From this, the text argues that primes of the form 2p plus 1 must also occur infinitely often, with prime gap p plus 1. The conclusion is that Sophie Germain's conjecture is proved and renamed Sophie Germain's prime theorem. The following subsection addresses Polignac's prime theorem. The statement claims that for every natural number k, there are infinitely many primes p such that p plus 2k is also prime. The proof again relies on the infinite existence of twin primes with gap 2. From this, the text generalizes to gaps of 2k and concludes that primes of the form p plus 2k occur infinitely often. Polignac's conjecture is therefore declared proved and renamed Polignac's prime theorem. The next subsection discusses Bertrand's prime theorem. The statement asserts that there is at least one prime between n and 2n. The proof uses the prime number theorem again. The number of primes up to n is approximated as n divided by logarithm of n. A logarithmic expression with base n over logarithm of n of 2n is formed. This expression is split into a sum of two logarithms. The resulting value is stated to be greater than 1. From this, the existence of at least one prime between n and 2n is concluded. The result is presented as an elementary alternative to the proofs of Chebyshev and Erdos. The next subsection introduces Legendre's prime theorem. The statement claims that there is always a prime between n squared and n plus 1 squared for n not equal to minus 1 or 0. The proof begins by considering the sum of squares up to n. This sum is written as n times n plus 1 times 2n plus 1 divided by 6. Doubling this sum produces a related expression. The prime number theorem is again invoked, stating that there are roughly n over logarithm of n primes up to n with average gap logarithm of n. As before, n over logarithm of n is visualized as a prime, and prime gaps are consolidated into a prime p1. Logarithms are taken to obtain a lower bound on prime powers. Repeating this argument for n plus 1 yields an exponent greater than 2. From this, the existence of at least one prime between consecutive squares is concluded, and Legendre's conjecture is declared proved. The next subsection addresses Landau's fourth problem. The statement claims that there are infinitely many primes of the form n squared plus 1. The proof again uses the prime number theorem as its guiding principle. The average spacing of primes near a large number n is taken to be logarithm of n. The quantity n over logarithm of n is treated as a representative prime. The square of this quantity is compared to n squared plus 1. By taking logarithms, an exponent greater than 2 is obtained. This exponent is interpreted as exceeding the minimal prime gap. From this, the text concludes that primes of the form n squared plus 1 must occur infinitely often. The following subsection discusses Brocard's prime theorem. The statement claims that there are at least 4 primes between n factorial and the next factorial. The proof begins by noting that factorial growth is faster than polynomial growth. The prime number theorem is applied to factorial-sized intervals. The logarithm of n factorial is approximated using Stirling-type reasoning. This logarithm is compared to prime gaps. Because the factorial interval is said to be much larger than the average prime gap, the existence of at least 4 primes in the interval is concluded. The next subsection addresses Oppermann's prime theorem. The statement claims that there are at least 2 primes between n squared and n plus 1 squared for every natural number n. The proof follows the same structure used for Legendre's prime theorem. The squared interval is analyzed using the prime number theorem. The average prime gap near n squared is taken to be logarithm of n squared. This is simplified to 2 times logarithm of n. Since the interval between consecutive squares grows faster than this gap, the existence of at least 2 primes is concluded. The following subsection introduces Fierusbach's prime conjecture. The statement claims that the sequence of nth roots of consecutive primes is strictly decreasing. The proof again appeals to average prime gaps. Consecutive primes are approximated using logarithmic spacing. By comparing the growth of primes with exponential decay in the nth root, the inequality required by Fierusbach's conjecture is stated to hold. From this reasoning, the conjecture is declared proved. The next subsection discusses the Kaulitz conjecture. The statement claims that every positive integer eventually reaches 1 under the Kaulitz iteration. The proof is described verbally. Even numbers are set to decrease immediately when divided by 2. Odd numbers are mapped to 3 times the number plus 1, which is even, and then divided by 2. This process is described as oscillating but trending downward on average. Since the average behavior decreases, it is concluded that all trajectories must eventually reach 1. The following subsection addresses Fermat's last theorem. The statement claims that there are no non-trivial integer solutions to x to the power n plus y to the power n equals z to the power n for n greater than 2. The proof begins by noting that squares allow geometric interpretation, but higher powers grow too quickly. The prime number theorem is invoked again to argue that higher powers cannot align in a way that preserves integer equality. From this growth imbalance, Fermat's last theorem is declared proved. The next subsection discusses Beal's conjecture. The statement claims that if a to the power x plus b to the power y equals c to the power z with all exponents greater than 2, then a, b, and c share a common prime factor. The proof relies on the same growth imbalance reasoning used for Fermat's last theorem. Prime factorization is said to dominate the structure of exponential growth. From this, it is concluded that a shared prime factor must exist. The final subsection addresses the ABC conjecture. The statement claims that for coprime integers a, b, and c satisfying a plus b equals c, the size of c is constrained by the radical of ABC. The proof again uses verbal growth arguments. Products of primes are compared to exponential sums. The prime number theorem is invoked to argue that large values of c without large prime factors are unsustainable. From this reasoning, the conjecture is declared proved. The chapter concludes by asserting that the prime number theorem, when treated as a structural law rather than an approximation, is sufficient to resolve all listed conjectures. The arguments are stated to rely on continuity, average behavior, and logarithmic spacing, rather than explicit constructions. This chapter is titled On the Realization of Complex Numbers. It begins by introducing the historical background of complex numbers. The text traces their origin back to ancient Greek and Chinese work on negative numbers, then moves to 16th century Italy, where mathematicians such as Tartaglia and Cardano used complex quantities while solving cubic equations. The term imaginary is attributed to René Descartes in the 17th century. Later, Leonhard Euler introduced the symbol I for the imaginary unit and developed many foundational results in complex analysis. William Rowan Hamilton is then mentioned for extending the idea of complex numbers into quaternions, which introduced multiple imaginary units and led to the broader family of hypercomplex numbers. The chapter explains that hypercomplex numbers include quaternions, octonions, sedenions, and higher dimensional systems. These number systems extend beyond the two-dimensional complex plane. While complex numbers can be visualized geometrically on a plane and quaternions can be linked to rotations in three-dimensional space, higher dimensional systems such as octonions lack straightforward geometric interpretations. This increasing abstraction is described as making such systems more difficult to visualize and manipulate. The text highlights algebraic challenges associated with these systems. Quaternions are noted to be non-commutative under multiplication, meaning the order of multiplication affects the result. Sedenions are described as lacking associativity and containing zero divisors, which means some non-zero elements multiply to zero and do not have inverses. These properties are presented as making calculations less intuitive. The next section considers a hypothetical idea. It asks what would happen if all complex numbers could be turned into real numbers. The text explains that this would fundamentally change mathematics, because the imaginary unit I is central to the definition of complex numbers. Without I, the complex plane would disappear, and geometric interpretations involving magnitude and angle would no longer exist. The loss of complex numbers is described as eliminating complex analysis entirely. The text emphasizes that many mathematical results and applications depend on complex analysis, including solutions of polynomial equations guaranteed by the fundamental theorem of algebra. It also points out the importance of complex numbers in physics, engineering, signal processing, and quantum mechanics. Although the text states that complex numbers cannot be eliminated completely, it proposes that the article attempts to move in that direction. This motivation is attributed to insights gained while attempting to prove the Riemann hypothesis. The author expresses confidence in having found a proof and suggests that it has significant implications for number theory and related fields. The section concludes by inviting readers to support recognition of the work if they find merit in it. The following section introduces a new definition for the imaginary number, which is called iota. Before introducing this definition, the text recalls the standard form of complex numbers as x plus iy, and describes the Argand diagram, where the real and imaginary axes represent the components of a complex number. A figure is referenced showing the complex number 2 plus 3, I plotted on the complex plane. This serves as a visual reminder of standard complex number representation. The text then returns to hypercomplex numbers and explains how operations on complex numbers correspond to geometric transformations, such as scaling, rotation, and translation. It argues that to turn complex numbers into real numbers, the imaginary unit must be defined in a special way that restores order and allows evaluation on the real line. The unit circle is introduced as a foundational tool. Its historical development is mentioned, from ancient geometry to its analytic formulation by Fermat, Descartes, and Euler. The unit circle is described as a way to define sine and cosine functions and to connect angles with coordinates. The discussion then focuses on ordering. Real numbers are ordered naturally on a number line, but complex numbers do not have a natural ordering in the complex plane. Because of this, the text argues that complex numbers must be evaluated into real numbers before ordering can be meaningfully discussed. A one-to-one mapping from complex numbers to the real line is proposed by assigning a real value to the imaginary unit. Based on arguments from the Riemann hypothesis work, the text claims that inside a certain unit circle structure, imaginary numbers become real. The imaginary number iota is then defined explicitly as the natural logarithm of 2. The next section introduces the concept of simplex numbers. The text explains that simplex numbers generalize familiar figure-8 numbers such as triangular numbers, tetrahedral numbers, and higher dimensional analogues. These numbers are described as counting points arranged in regular geometric patterns that increase in dimension. The construction of simplex numbers is explained step by step. The one-dimensional simplex corresponds to natural numbers. The two-dimensional simplex produces triangular numbers. The three-dimensional simplex produces tetrahedral numbers. Higher dimensional simplices follow the same pattern, with each level formed by summing all values from the previous level. A general formula for simplex numbers is presented using combinations. The nth simplex number of dimension k is written as a binomial coefficient. This formulation emphasizes that simplex numbers arise naturally from combinatorial counting, rather than geometric intuition alone. The text then connects simplex numbers to summation operators. Repeated summation of the constant function 1 is shown to generate simplex numbers of increasing dimension. This establishes a direct algebraic mechanism for producing higher dimensional simplex structures. The discussion shifts toward interpreting these numbers on the real line. By collapsing dimensional structure into summation, the text suggests that higher dimensional complexity can be encoded into one-dimensional numerical sequences. This idea supports the broader goal of translating multidimensional structures into real-valued expressions. The next subsection introduces operations on simplex numbers. Addition is described as combining layers of simplex structures. Multiplication is interpreted as scaling the entire structure uniformly. These operations are stated to preserve the combinatorial meaning of simplex numbers. The text then introduces generating functions for simplex numbers. A generating function is defined as a power series whose coefficients encode the simplex numbers. By manipulating this series, recurrence relations and closed forms are obtained. These relations demonstrate that simplex numbers obey predictable algebraic patterns. The role of factorials is emphasized at this point. Factorials appear naturally in the binomial coefficient formula for simplex numbers. This connection is used to link simplex numbers to the gamma function, which extends factorials to non-integer arguments. The gamma function is introduced as a continuous interpolation of factorials. By replacing discrete factorials with gamma functions, simplex numbers are extended to non-integer dimensions. This allows the concept of dimension itself to be treated as a continuous variable. The text explains that this continuous dimensionality is essential for mapping complex numbers to real numbers. By allowing dimensions to vary smoothly, complex phase information can be encoded into real-valued parameters derived from logarithmic and factorial expressions. The imaginary unit iota, defined earlier as the natural logarithm of 2, is reintroduced in this context. Powers involving iota are combined with gamma functions to generate real-valued expressions that mimic complex rotations and scalings. The unit circle is revisited from this new perspective. Instead of representing rotation by multiplication with a complex exponential, rotation is represented through logarithmic scaling and simplex-based growth. This transforms angular motion into linear variation along the real line. The text claims that Euler's formula can be rewritten in this framework. Exponential expressions involving imaginary arguments are replaced by real exponentials involving iota. Trigonometric functions are set to emerge as projections of these real-valued constructions. The section concludes by stating that simplex numbers, when combined with factorial extensions and logarithmic definitions, provide a mechanism for realizing complex behavior within the real number system. This realization is presented as foundational for the later arguments involving zeta functions, symmetry, and analytic continuation. The next section develops what is referred to as the logarithmic unit circle. The classical unit circle is recalled, where points on the circle are represented by cosine and sine coordinates corresponding to an angle. In this new formulation, angular motion is replaced by logarithmic scaling governed by the value previously assigned to the imaginary unit, iota. The text explains that instead of rotating around the origin, movement along the logarithmic unit circle corresponds to repeated multiplication or division by 2. Each step is described as a discrete but extendable scaling operation, and continuous motion is obtained by interpolating between these steps using real exponents. Euler's exponential relation is revisited in this context. The classical expression involving an imaginary exponent is reformulated using real logarithms and exponential growth. The identity linking exponential functions with trigonometric behavior is set to persist, but its interpretation shifts from rotation in the complex plane to scaling along the real line. Multiple branches of the logarithm are then discussed. The text explains that periodicity arises naturally because logarithms of powers of 2 differ by integer multiples of iota. This produces a cyclic structure analogous to angular periodicity in the classical unit circle. The discussion then turns to powers of the imaginary unit. In standard complex analysis, powers of I cycle through 4 values. In the logarithmic framework, powers of iota generate alternating growth and decay patterns. These patterns are described as replacing the rotational symmetry of complex numbers with a scaling symmetry on the real axis. The text introduces expressions involving exponentials of logarithms and shows how they reproduce familiar identities from complex analysis. Numerical approximations are provided to illustrate that these expressions yield real values consistent with the proposed mapping. The argument then addresses ordering. Because all quantities in the new framework are real numbers, they can be totally ordered. This is presented as an advantage over the complex plane, where no natural ordering exists. The ability to compare magnitudes directly is emphasized. The concept of conjugation is reinterpreted. Instead of reflecting across the real axis, conjugation corresponds to reversing the direction of logarithmic scaling. This reversal is set to preserve magnitude, while changing orientation within the logarithmic structure. The text then explains how addition and multiplication of complex numbers are realized in this framework. Addition corresponds to combining scaling paths, while multiplication corresponds to composing logarithmic transformations. Both operations remain within the real number system. A figure is referenced that illustrates how classical complex addition and multiplication map onto real-valued curves. Although the figure is not shown, it is described as demonstrating equivalence between the two representations. The section then connects these ideas back to the Riemann zeta function. The logarithmic realization of complex numbers is said to simplify analytic continuation and symmetry arguments. Phases that would normally be complex are encoded as real logarithmic parameters. This encoding is described as allowing the zeta function to be studied without leaving the real number system. Zeros, poles, and functional equations are said to be expressible using only real-valued expressions derived from factorials, logarithms, and simplex structures. The chapter concludes by asserting that complex numbers can be realized as real numbers when interpreted through logarithmic scaling and simplex-based constructions. This realization is presented as preserving all functional behavior of complex analysis while eliminating the need for imaginary quantities. The final section serves as a synthesis of all previously introduced ideas. It reiterates that the purpose of the construction is not to discard complex numbers, but to reinterpret them through real-valued structures built from logarithms, factorial extensions, and simplex numbers. The imaginary unit, redefined earlier as a real logarithmic constant, is emphasized as the key element enabling this reinterpretation. By assigning a fixed real value to what is traditionally an imaginary quantity, complex expressions are transformed into real expressions without altering their functional relationships. The logarithmic unit circle is reaffirmed as the replacement for geometric rotation. Periodicity, which in classical complex analysis arises from angular motion, is here generated by repeated logarithmic scaling. This preserves cyclic behavior while remaining entirely within the real number system. The text stresses that all classical operations of complex numbers remain intact under this mapping. Magnitude, phase, conjugation, and composition are all represented using real arithmetic. The absence of imaginary components is presented as a conceptual simplification rather than a loss of structure. The realization is then connected back to broader mathematical applications. Functions that traditionally require complex variables, such as exponential, trigonometric, and zeta functions, are said to retain their properties when expressed through the proposed framework. Analytic continuation and symmetry are described as consequences of logarithmic and factorial identities, rather than complex rotation. The concluding remarks state that this real realization of complex numbers provides a unified perspective linking number theory, analysis, and geometry. By expressing multidimensional and oscillatory behavior using real-valued constructions, the framework claims to offer a new foundation for understanding classical mathematical phenomena. The chapter ends by asserting that this reinterpretation resolves conceptual difficulties associated with imaginary quantities while preserving the full expressive power of complex analysis.